Hello students, welcome to today's lecture on artificial neural networks. So in our previous class, we have discussed about different types of learning paradigms. And today we will discuss about the learning algorithms or learning rules that will be used in neural networks. Let us start with why we need these learning rules, what are these learning rules, and how they are going to help us while designing the neural networks. Learning rule or learning algorithm is a method or algorithm or mathematical logic which improves the network's performance or training time. That means uh, if when you are training the artificial neural network, you require an algorithm or an approach to decide on how to train the corresponding neural network in such a way that in future, whenever we submit an input to the neural network, it will identify a correct output. Okay, so for that purpose, we require a training algorithm, and that is where these learning rules are useful. And uh, the learning rules may accept the existing conditions, that means the present weights and biases of the network, and we'll compare the expected result and actual result of the network uh, to give new improved values of weights and biases. So based on the present weights and biases and the target value, expected target value, the neural network will always try to adjust the corresponding weights to produce the target outputs. So that process is called as training or learning. Okay, and the learning rules decides how fast or how accurately the artificial neural network can be developed. Okay, so overall, the purpose of a learning algorithm or learning rule is to help the neural networks in training process. Okay, there are several types of learning rules available. Among those, only few are listed over here. It is not limited. Many other learning algorithms are also available, but in our syllabus we have only four learning algorithms. The first one is Hebbian learning rule. Second one is error correction learning. Third one is memory-based learning, and fourth one is competitive learning. We have only these four in our syllabus, and there is a Boltzmann learning rule, perceptron learning rule, and so on. Many other learning rules are available. I did not list down all those here. Anyhow, we'll be discussing only the first four learning rules in our lecture schedules. Let us start with the first learning rule, Hebbian learning rule. Hebbian learning rule, which is also called as Hebb's learning rule, was proposed by Donald O. Hebb. This will be treated as this learning rule will be treated as the oldest learning rule among all the rules, and it is also an easiest learning rules used in the neural networks. Generally, these learning rules are useful in pattern classification. Particularly, this Hebbian learning rule is useful in pattern classification, uh, which makes use of a single layer neural network. That means one input layer and one output layer. And Hebbian rule works by updating the weights between neurons in the neural network for each training sample given to the neural network. Okay, so once all the training samples are completed, we can treat the corresponding neural network trained. So this is the Hebbian learning algorithm. What will happen is, uh, First step in the algorithm is to initialize all the weights, including bias, to 0. So every weight in the neural network will be initialized to 0 along with the bias weight also. The second step is for each input vector S and target vector, the corresponding target vector, 3 steps will be repeated. The first step is set activations for input units with the input vector xi is equal to si for I is equal to 1 to n. That means we'll consider one input vector at a time, and then set the corresponding output value to the output neuron, that is y is equal to t, where t is the target value expected for this input vector xi. So after setting the input vector and target value, update weight and bias by applying Hebb's rule for all I is equal to 1 to n, where n is the number of inputs. By using the formula, you need to remember this formula. Wi of new, that means the new weight will be calculated as Wi of old plus xi into y, where Wi of old is the existing weight connecting the neurons, plus the xi is the input vector, and y is the target output, xi into y. For example, if you are calculating the new weight with respect to the input vector x1, then the formula becomes w1 of new is equals to w1 of old plus x1 into y. And y is the corresponding output expected from the input vector x1. Okay. And also biases will be updated as well. New bias value b of new is equals to old bias value, that is b of old plus y, the target value. Okay, so we can merge these two formulas into one also with the help of the vector operations. We'll see it when we go through an example how these two can be combined into a single formula using vector operations, vector multiplications. Okay, so this is the algorithm used in Hebb's learning rule. So I'll repeat it again quickly. Set all the weights to 0, including bias. Consider one input vector at a time, and for each input vector, the target vector will also be given. For each input vector and target vector combination, find out the new weights using the formula Wi of new is equals to Wi of old plus xi into y. Okay, so this is the formula we are going to make use. Now let us see the working of Hebb's rule with the help of an example. I'm considering a simple example here that resembles AND gate. We need to understand this table first. The first vector is x1, -1, -1, 1 will become the first input vector, where x1, small x1 is going to be the first input, small x2 is going to be the second input. That means the neuron is having two input connections and a bias connection. Okay, so two inputs plus bias is going to be the input vector. This entire thing forms an input vector, capital X1. Okay, and the corresponding output value for this is -1. Okay, so that means capital X1 is the input vector that represents -1, -1, 1, and its corresponding target value is -1. Similarly, the second input vector is -1, 1, 1, and the corresponding target value is -1. And third input vector, capital X3, is capital 1, -1, 1, and its target value is -1. And the fourth input vector is 1, 1, 1, and the target value is 1. If you replace these minus ones by zeros, then you can see that this is x1, x2, y is nothing but an AND gate. The behavior of AND gate is replicated here, except that 0 is replaced by -1. So we can call it as a bipolar AND gate. Okay. So I want to design a Hebbian neural network to identify the target value for a given input values. That means if I give -1 comma -1 as inputs to the neuron, the output from the neuron should be -1. In such a way, I'm going to design. Similarly, if the input given to the neuron is -1 and 1, the neuron should identify the output as -1. And if the input given to the neuron is 1 and -1, the neuron's output should be -1. And finally, if the input given to the neuron is 1 and 1, the target value, the output value produced by the neuron should be 1. So it should produce, the neuron should produce these values when these outputs are given. The corresponding output should be produced. This bias is given as 1 over here. You can take any value between 0 and 1 as bias. So now let us understand the design process for this given AND gate. So we know that there are 4 training samples. As I told, there are 4 training samples, capital X1, capital X2, capital X3, and capital X4, representing -1, -1, 1, -1, 1, 1, 1, -1, 1, and 1, 1, 1. These are 4 training samples along with the target values. Also, we assume a bipolar step function because we want to produce 2 values, -1 and 1. Binary step function produces 0 and 1. Because we require -1, 1 and 1, we take it as bipolar step function. Okay. So you need to assume this activation function also based on the outputs that are to be produced by your neural network. So because the outputs to be produced is -1 and 1, I assume this bipolar step function as activation function. Okay. All right, let us begin this. Since there are 4 training samples, you require 4 iterations to design your neural network. Okay. Let us start with our algorithm. The first step of our algorithm is to initialize all the weights and biases to 0. That means the weight vector W is equals to 0, 0, 0 transpose, because I wrote it as a single row over here, but vector is a single column. Therefore, the transpose gives us the single column vector. Okay, and the bias is also initialized to 0. Actually, this contains the bias also. The third value is bias 0. Okay, and set input vector xi is equal to si for I is equal to 1 to 4. That means x1 is equal to first input vector -1, -1, 1. Even though it is written as a row, its transpose will give it as a vector, a column vector, because as I told you, the definition of a vector, it's a single column from a matrix. So to make it a column vector, it is taken the transpose over here. X2 is -1, 1, X3 is 1, -1, 1, and X4 is 1, 1, 1. Okay. These are the values we took from this table only. -1, -1, 1 is the first vector, and so on. Okay, so after initializing these vectors, set the corresponding target value also to y. That means y1 is going to be -1 based on this. Y1 is going to be -1, y2 is going to be -1, y3 is going to be -1, and y4 is going to be 1. Now let us start designing it. In first iteration, we will calculate all the three weights including bias by using the formula W of new is equals to W of old plus X1 into Y1. So in first iteration, we will be considering the first input vector, that is X1. Okay. So what is W of old till now? It is zeros only. So 000 to the power t plus X1 is -1 minus 1 1 to the power t into Y1 is -1, the target value. So after multiplying these values, we will get a vector 1 1 minus 1. That means weights are updated now. The W1 is 1, W2 is 1, and bias becomes 0. Okay. So for the second iteration, we will consider this as weight matrix. Okay. Initially weights are 0, so we considered it 0 here as weight matrix for the first iteration. For the second iteration, weights are updated now. It is 1 1 minus 1 transpose. So you need to consider this updated weight matrix for the second iteration. Right now, W of new second iteration is calculated like this. W of new is equal to W of old is now 1 1 minus 1 plus consider the second vector, second input vector, that is -1 1 1 into the target value for second one, that is Y2 -1. Okay. So this will give us the values 2 0 minus 2 power t. Okay. Now these are the new weights. We need to consider these weights for the third iteration. W of new is equals to the new weights from second iteration plus third input vector. You can see the third input vector is 1 minus 1 1 power t. So we'll consider third input vector for third iteration into the target value, that is Y3. So what is Y3 here? -1. Okay. So we'll consider it as Y3. After performing the corresponding operation, we will get 1 1 minus 3 over here. And in fourth iteration, we will consider these weights, updated weights, 1 1 minus 3 plus fourth input vector. What is fourth input vector here? 1 1 1. We will consider fourth input vector into fourth target value. So corresponding target value Y4 is 1 only. So we will use 1 here. After performing these operations, we will get the weight vector as 2 2 minus 2 over here. So the final weight vector that we got is 2 2 minus 2. That means the inputs, that is W1 is 2 connecting to the neuron, W2 is 2, and the bias weight is -2. Initially we started with 0 0 0. Now the weights were updated as 2 2 minus 2. So now, because there are no more input vectors, we can say that the training of neural network is completed. And for a given input X1 and X2, if it can identify the corresponding target value now, then we can say that the design of this neural network is successful. Okay, now let us test this neural network with some input samples. Okay, let us start with the first input sample. The first input sample is -1 -1 I am taking, and bias is anyhow 1. B is going to be 1. This is going to be always 1. Bias weight is -2. Okay, bias is 1, bias weight is -2. Don't forget that difference. These are weights and these are inputs. Okay, now for this -1 -1 1 combination, let us calculate the y value as, so -1 -1 1 given as inputs. So now calculate -1 into 2 plus -1 into 2 plus 1 into -2. So we'll get -2 -2 -2. That is going to be -6 as output from this neuron, and this -6 will be given to the activation function. As I told you, the activation function that we assumed is a bipolar step function. So bipolar step function takes this -6 and produces -1 because it is defined like this. If x is less than 0, that means if input given for the function is less than 0, then the output is going to be -1. So it produces -1 for all the negative values. Similarly, you can calculate the value produced by the neural network for the second input combination -1 and 1 with bias 1. We can calculate it. It will produce -2 over here. When -2 is given to the binary step form, bipolar step function, f of -2 is going to be -1, because if it is a negative value, the output will be -1. Similarly, for the remaining two also, the output value is calculated as -1 and +1. If you observe the target values for each given input vector, we are able to produce the correct output over here: -1, -1, -1, +1. Therefore, we can say that the neural network is designed properly for the bipolar AND gate behavior. Okay. So that is how Hebbian rule can be used to design our neural network for a given scenario. Right. So once we are done with our design of neural network, we can draw a decision boundary based on the weights that we got over there. The weight vector is 2, 2, -2. Therefore, the formula becomes 2x1 plus 2x2 minus 2b is equals to y. That means the target is calculated as 2x1 plus 2x2 minus 2b. That is the formula. Let us replace this y with 0 to get an equation for the line. So we'll get 2x1 plus 2x2 minus 2b is equals to 0. And by taking 2 out, we'll get x1 plus x2 minus 1 is equals to 0. And finally, we get 2 into x1 plus x2 is equal to 2, which will produce x2 is equals to minus x1 plus 1. You can draw this x2 is equal to minus x1 plus 1 into your graph like this. That separates all the minuses towards one side and plus towards another side. Okay, so it is a clear separation of positive values and negative values in this decision boundary. Okay. So if separation can be done like this, we can call it as a linear decision boundary. Okay. So based on this knowledge that we learned till now, here is an exercise for all of you. Try to design a Hebbian network for OR gate. That means you need to consider the table here. This is going to be same, x1, x2 bias. These are all going to be same. The target values will be changed. So in OR gate, whenever the input is 0 and 0, then the target will be 0. That means this becomes -1 only. And all the remaining three, these three are going to be plus ones, positive ones. Okay. Just change these target values as, keep this as -1 and all the remaining three values as plus ones. Okay. That will become an OR gate, bipolar OR gate truth table. And then try to design a Hebbian network by using these steps, by following these steps, and draw this diagram and also draw the decision boundary for the bipolar OR gate. It's not OR gate, for bipolar OR gate. Okay, so I hope you can do that. If you get any doubts while designing this Hebbian network for OR gate, you can approach me either through mail or you can contact me on Monday in college. Thank you all for your patient listening. That's all for today. We'll come up with another learning rule in our next session. Thank you all again.